Greetings, everyone. Let's talk the fundamental theorem of calculus. This is going to be very important for the AP Calculus exam. It's fundamental. It's going to be all over the place, as I've mentioned a lot recently. And so I just wanted to give you an overview of how you're going to see it on the AP exam so that you're ready to handle it in the several different forms that it will come in. So let's take a look at the fundamental theorem really quickly, and then we'll get into some examples. So we have the function f of x continuous on the closed interval a, b. And then we have two parts to it. The first part is this idea about the integral and the derivative being inverse relations to each other. And if the function is continuous, then essentially the integral and the derivative will cancel with each other. And there's a little bit of a caveat. Notice that the integrand here is in terms of some other variable t, and we're differentiating with respect to x. And the integral is a function of x with the upper limit of integration, x. And so when we take its derivative and work this out, what we're going to end up doing is replacing the t that's in the integrand with x, and the answer is just going to be f of x. The answer is going to be a function of x. We'll look at some examples of that in a moment. Part two is what we called at one other point the evaluation theorem, because that's what our book calls it, but it is the way we evaluate a definite integral by using an antiderivative. And so if we have the definite integral from a to b of f prime of x dx, we're going to take the antiderivative of f prime, or really any antiderivative of f prime, and then we're going to substitute or evaluate it at b, evaluate the antiderivative at a, and then we're going to subtract the two, f of b minus f of a. And this is a form that's been coming up a lot in some of the practice problems we've been working on lately. And so we're actually going to look at that one first. And so here's an example. Typical example, I'm using velocity and position because they're familiar with us, and we should have a sense of what's going on, but we're going to generalize this to the relationship that's important that we're going to get out of this. So let v of t be equal to negative 2t plus 8 be the velocity of an object at time t, and let the position of the object be 12 at t equals 3. I'm not putting any units in the problem because right now units don't matter, but be aware that on the AP exam you'll often see a or a comma followed by a remark saying where v is measured in feet per second or miles per hour or some other units, and you just kind of read through that, make sure you know what the units are being used and the relationships that are there, but for our purposes right now, their specific units are not important. All right, so we're asked to find the object. What is the object's position at t equals 10. Now, the connection here that we're trying to make, we could just find the position function. We can do that by taking the antiderivative of v, and this is an easy velocity function, so we can take its antiderivative rather easily and work this out as just finding the position function, finding the constant of integration and whatnot. But I want to look at this from the perspective of the fundamental theorem, because this often comes up in a calculator section where the integrand is more challenging to take the antiderivative of, and so I want you to think about this in terms of the fundamental theorem. So the key thing here is we're given a rate, okay, that's our v of t, and that's the rate of change of position, and we know the position at a certain time, and we want to find the position at another time. Those aspects of the problem should be firing those signals in your brain saying, oh, this is a fundamental theorem problem, okay? I have a rate of change of some quantity, and I want to know the quantity itself at a certain time, and I already know the quantity at some certain time as well. So those three things are going to be the aspects that we're looking for the fundamental theorem, or in which to use the fundamental theorem. So let's go ahead and set this up. By the fundamental theorem, if we took the indefinite integral, and I'll put some limits on this in just a moment, of v of t dt, now I'm going to end up with something related to the position of the object. Now, to choose the upper and lower limits of integration, we have to use the information that we were given. We were given some information at t equals 3, and we want information about what's happening at t equals 10. So that's why we're choosing those as our upper and lower limits of integration. It's based on the information that we have. Now, we should know from the fundamental theorem or the evaluation theorem that to evaluate this, we're going to use an antiderivative, And the antiderivative that we're going to use, well, of course, the antiderivative of velocity is position. And so this is going to be x of 10, or s, or whatever the chosen variable for position is, p, even if you like that one. It's going to be x of 10 minus x of 3. And this is what we're going to have to solve, okay? We're looking for, specifically, this one right here, x of 10. We know x of 3. This is the one that was given to us, okay? So we know that that's 12. And the integrand, or the integral on the left-hand side of the equation, we need to evaluate that. Now, if you were in the middle of the calculator portion of the AP exam, then you just take that integral and evaluate it on your calculator and get a number for it. Because remember, the definite integral represents a number. And I don't want you to try to mess with trying to find an antiderivative for a function, even if it is relatively simple on the calculator portion, because the AP examiners are not expecting you to use your, the technique by hand. They are expecting you to use your calculator, and they're not giving you the extra time to do it by hand. They time and pace the problems for you to do the calculator section, at least certain parts of it, with the calculator. And so there's no extra time to sit here and mess with finding the antiderivative on your own unless they say to, or it's a non-calculator section. If it is the calculator section, just evaluate this. So on the left-hand side, we're going to we would have to do that on our calculator. But for now, since I don't have a calculator handy, let's go ahead and work this out. So we're going to get the integral from 3 to 10 of this negative 2t plus 8 dt, and we'll find an antiderivative of it, and we're going to get negative t squared plus 8t. We don't need a constant of integration because it's a definite integral. We'll evaluate it from 3 to 10, and then we're going to get, let's see, we're going to get negative 100 plus 80 when I plug in 10, minus, and when I plug in 3, I'm going to get negative 9 plus 24. And so this is going to work out to be negative 20 minus 15. And so negative 35. Now again, you would do this on your calculator if this was a calculator section of the exam. And so I got negative 35 equal to x of 10, the position at 10, minus x of 3, which I believe is 12, although I should scroll down and take a look. Yes, it was 12. And we just add 12 to both sides, and we get x of 10 is equal to negative 23, and that would be the answer to the question. So again, the key to set this up is by seeing this as you're given the function that is the rate of change of a quantity, and you know the value of the quantity that's changing at a certain time, and you want to know the value of the quantity that's changing at a different time. And so we set this up using the fundamental theorem. Now, in our notes, when I gave you that printed out, typed up set of notes, I would have written it like this, or I did write it like this in those notes. X of 10 is going to be equal to x of 3 plus, what did I write it as? X to the third power, excuse me. X of 3 plus the integral from 3 to 10 of x prime of t dt. This is that fundamental theorem relationship that I put in that on that type sheet. The net change in this would be the net change in position, and we're trying to find, well, this part is the net change in position, but we're trying to use that net change in position and add it to the initial position at 3 to figure out the position at 10. So this is that relationship that we were using. More generally, it's going to look like this. If I integrate the rate, okay, the rate being f prime of x dx on the interval from a to b, then I could find f of b, or I know that's going to be f of b minus f of a, so I could find f of b by just rearranging this as f of a plus the integral from a to b of f prime of x dx. And with that right there, that's how we find the position at some point. We could also solve it for f of a if we wanted to, just doing a little bit of different algebra. F of a would be equal to f of b minus the integral from a to b of f prime of x dx. We had one of these happen on a torture session earlier this week. But both of those are valid equations to solve for one of the positions. If you know the upper or you know the lower, you want to find the other. That's how you can work this out. So here's one more example. If the volume of water in a tank is changing at a rate of r of t equals 10 sine root t plus 5, and the volume of water in the tank at t equals 2 is 75, what is the volume at t equals 8? Now, we're not going to complete this problem together right now, but we'll set it up, and then I'm just going to tell you to go ahead and work the rest out on your calculator and get an answer for this. But again, here's the same idea happening. We know how the volume of water is changing, okay? Changing at the rate. So R is a rate, okay? That's a key word that we got to make sure we read for. So this is the rate of change of the volume. Technically, this is dV dt if you want to rewrite it in calculus notation. But not all the problems always give you the rates in calculus notation. They just can give you as a function name, in this case R. And so we know the derivative of the volume function, and then we know the volume at a certain time, and we want to know the volume at another time. So this is fundamental theorem happening here again. And so we could set this up as, if it's easier for you to set it up in the original form of the fundamental theorem, then go right ahead. So we're going to do a definite integral from 2 to 8, and we're going to integrate the rate, r of t dt, and that's going to give us the volume at 8 minus the volume at 2, and we want to find the volume at 8. And so that's the key to the setup right there. Some of you may want to jump right into rewriting it in the form that I put on the that net change in set of notes. And so you might write it like this: v of 8 is equal to v of 2 plus the definite integral from 2 to 8 of r of t dt. Either way, it doesn't really matter. The key thing here is that we recognize that this is the pattern that we need to use to solve the problem, because we know the amount at 2, and then we know the amount that's the net change in the amount that's going to happen from 2 to 8. Okay, so if this is accompanied by a question like interpret what this means, okay, the integral part represents how much the amount of water that is going to either be increased or decreased. It's the net change in the amount of water. And so when you evaluate that on your calculator, which you are going to do here on your own, you're getting the net change in the amount of water. So if you get a positive number, that means the amount of water went up from 2 to 8, increased by that amount. And if you get a negative number, that means the amount of water went down by that amount. Okay, so I don't know because I just made the problem up and didn't work it out. Okay, but you can do the rest on your own. So you know v of 2 is 75, and so you'll set this up as v of 8 is equal to 75 plus, and then you're going to run this through your calculator, the integral from 2 to 8 of this r of t. Evaluate that on your calculator, and then you'll know what v of 8 is, and you'll know the amount of water in the tank at that time. Alright, let's take a look at the first part of the fundamental theorem. So if I have g of x defined as an integral, and I want to take the derivative, okay, so I want to find g prime, then the first part of the fundamental theorem just says that the integral and the derivative are going to cancel with each other, and I'm going to replace the t's that are in the integrand, which there's only one, with the x, and that's going to be the answer right there. It's really most of the time that straightforward, okay? But there are times when they do make the function a little bit different. So say we had h of x, and I'm going to use the same exact integrand here, but I'm going to change the upper limit of integration to x squared, and then we're going to have root 2 t squared plus 1 dt here. And if we want to find h prime, this is essentially the same problem. I still need to take the x squared and put it in place of the t that's sitting right here, just like I did for g when I took its derivative. But because I'm not just, my upper limit of integration is not just x squared, I don't want to just stop there. I got to apply the chain rule, and because my inner function is x squared, and I'm going to need to take the derivative of the x squared as well. So when I work out x prime of x, h prime of x, we're going to get the square root of 2 times x squared squared plus 1, because again I'm replacing t with x squared, and I'm going to have to square that result. And then all that has to be multiplied by the derivative of x squared, so we get times 2x. And then that's it. That's how you handle that first part of the fundamental theorem. If you just think simply about it and remember this relationship, it's a fairly straightforward problem. On the AP, they don't get overly complicated with this. They may do, at most, as far as I've seen in the past, I mean, they could do something a lot worse, but just they never have. I mean, they could put the variable limit of integration on the bottom here and put this as a 2 or something like this, and then put, I don't know, let's put e to the t cubed dt here or something like that. We can't jump right into the fundamental theorem immediately. We have to switch the upper and lower limits of integration, like this, and then we can go ahead and apply the fundamental theorem, because we need the pattern to match. And so here the pattern matches where the variable is on the upper limit of integration and the constant is in the lower limit of integration. And so this is going to become negative e to the x cubed. Now we're taking a derivative, so there's no plus c here. I know some people tell you don't forget the plus c. This is not the case where we need a plus c, because in taking a derivative, all constants go to 0, so there's no plus c that occurs on this. And essentially that's as hard as the fundamental theorem gets on the AP. So you can go look up in the book, section 5.3, section 5.4. We'll have examples related to this sort of stuff. And watch the video again. Go look at the examples that we gave you from the practice exam and from the other torture sessions that we've been doing this week, and get yourself ready for these types of problems, because the fundamental theorem is going to be a big deal on the AP exam. Go study.